Okay, so I will continue now with my talk. Yeah, it's a big thing. I'm not sure what I have, what I was thinking when I made the timetable. I put myself right between Stefan and Jim, two two big names. This will be a quick talk about is Julia ready to be adopted by HEP? Let me reload this site. It's more like a personal story, including some of our findings of recently published paper. Let me go to full screen mode. Okay, this will work. Okay, so my name is Tamas Gal. You can just call me Tom. It's easier. It's also the nickname. Oh yeah,
you're not sharing yet.
Let me show my screen. No, it should be fine. Oh. I'm not really handy with Windows. Where is this? And full screen is here. Okay, so my name is Tamas Gal. You can simply call me Tom. That's also my nickname in Hungarian. This is a talk which I more or less gave also at the HEP conference. There are a lot of people who worked on the contents and stuff. I listed a few names, but we're more people actually. Okay, let me start with my first encounter with the HEP software world, which was somewhere around 2012 or so. I started as a graduate student and research assistant here at ECAP in another building actually, but like 200 meters to the west from here. And my first job was like, well, I came to the building and thought about doing something in the high energy physics world or particle physics world or astroparticle physics world especially. And my first job was related to the Antares neutrino detector, and this was my first encounter with the root based framework, which was, by the way, a nightmare to install on my MacBook, which was running macOS 10.6 back then. Yeah, and I was wondering, so before that I worked in the optics and I worked with C++. I worked on GPU code and accelerating graphics ray tracing software for phase measurement deflectometry. But here in the HEP world, obviously root was a big thing. So I started to learn this root thing and I got really in big trouble. So this was something very new to me to work with an extremely large software. Before that, I worked with small projects and some more C++ code, etc., and some MATLAB code, etc. But then now I had this very big project. And I had something like 15 years of self-taught coding experience and in different programming languages. So I'm already programming since I'm a child, basically. But for me, it was a real challenge. And I spent a lot of days, a lot of weeks to get my first results, which were presentable, and it was quite embarrassing how long it took. And one of the reasons was that it was really hard to get access to this data. It was not really well documented in that sense. It was very hard to work with. I couldn't really use my MacBook, so I had to work on cluster machines or other machines and then do all this X forwarding and transferring data back and forth. And yeah, there were also a lot of caveats. And so for me, it was a real challenge. And yeah, most of my fellow students had a much worse starting situation because they didn't even know how to code. So as a physicist, and at least in Germany, and I know in many other countries, you don't really learn how to write code or how to program or what a compiler is, etc. So I already had a big step there. But most of my other colleagues had none. So they kind of learned this root style of doing things, which were just writing a big, long main function, which was more like a script. And doing some things, and their work often got simply neglected after a while, because they completely lost track how things are working, and yeah, it was really not meant for reproducible work. Then Python came to rescue, and this was really funny because I have used Python for a long time before that. mainly as a shell replacement for doing computer administration. And then I realized I can use it in science as well. So there was like the first versions of matplotlib and NumPy came to the world basically. And yeah, I really enjoyed it, and I decided to work a lot on high-level Python tools to reduce all these boilerplates needed to make some plots and some analysis, and to make things more accessible and to exploit all the benefits of this interactiveness to lower the entry barrier, especially for newcomers. So I was also supervising new students, bachelor students and master students back then. Yeah, and it was a lot of fun for me at least. And the years after, so I joined Came3net. I started in Antares, as I said, but then I quickly came to Came3net, where I also did my diploma thesis. And I really pushed hard for Python. I was the Python guy, and I wrote a lot of library code and packages in Came3net. I still do maintain many of them. And I wrote high-level stuff and low-level stuff, so all kind of stuff, like on the hit level, like K40 coincidence calibrations for time calibrations, but also high-level analysis, big data and machine learning stuff, and introduced also other formats in Came3net like HDF5. And I also convinced many people that Python is able to compete with all the compile drivers in Came3net. So we have one big chunk of a framework which is based on C++ and root, and kind of the older generations in Came3net say you should do everything in this framework, but it's an extremely complicated or complex framework with, I think, hundreds of classes, hundreds of templated classes with lots of hierarchical stuff. And yeah, it's really hard for someone to get things done. So most of the time, students come to our experiment, they stay a few months, they finish their bachelor or master thesis, and then they go. So many of them spend like months until they get something done. And with these Python tools, it was really much easier for them to get things done and make them work. And of course, all these virtual environments are really nice. So you don't have this stuff like you want to use multiple C++ packages and you have to link them together, you make them work together, compile them together, etc. Because Python, of course, has this package management system, etc. But the problem was that we ended up in a technological Mikado, as I call it, because the problem is that, of course, Python comes with this so-called two-language problem. We all know that Python is not a high-performance language, and crafting high-performance code in Python is really demanding. So it really requires a profound understanding of the computer architecture, of languages interdependencies, and the art of producing reusable code libraries. And yeah, there are many solution attempts to tackle this two-language problem, and the maintenance overhead rapidly escalates with each additional technology, which are mandatory. I put a few examples on the right side. These are all stuff which I've worked on or which I still maintain in current projects. You really need at least a few of them if you want to make a Python application fast. And yeah, you can see there are different ways to glue C++ code or C code or Fortran code to Python, which is fast, and there are different ways to accelerate Python, etc. But they all come with caveats. And yeah, so Python is mostly used as a high-level layer. And of course, the problem is also that it kind of restricts access to the low-level modifications. We also know that loops in Python are a disaster, but they are a very, very familiar paradigm for many programmers out there. So it's very natural to think about these. And we kind of force people to think into these vectorized operations and do all these gymnastics with the stuff if they are using NumPy, for example, or stuff like this. Okay, so we have solutions, but they require a lot of compromises. And I realized that it's really hard to find new maintainers for my old libraries because they need to know all this other stuff. So it's not like, oh, a new bachelor student comes and he knows Python. Because he knows Python or she knows Python mostly means that they can do some NumPy stuff and some Panda stuff, but it doesn't mean that they know how to do bind 11 bindings or how to optimize number code or how to write Cython code or C extensions for Python. Okay, there are many reasons to switch languages, and I borrowed this nice graph on the top right from Jim, who will give the next talk, because I like it. It's kind of a timeline where you can see the assembly language being taken over slowly by Fortran, which was a big chunk and still present today, and then C++, and then finally Python in the 2000s and so on. So here I listed just some good reasons to switch languages. So if you go from assembly to Fortran, it was mostly this readability and the hardware independence. Of course, it was really cool to write code which can run on different architectures. Because we know if we write assembly, we use strict instructions for a specific CPU. In Fortran, the compiler does this stuff. And then, of course, if it gets more complex if you have nested data structures, C++ comes in quite handy. So this was probably one of the main reasons there was a shift from Fortran to C++. And then there's, of course, also Python, which gives you interactivity and this ease of use and packaging and all the stuff. So this is where I kind of encountered the high-energy physics world. Okay, here are some histograms I've scraped from GitHub, also based on the idea of Jim, by selecting people or trying to find GitHub users who are related to high-energy physics. So on the left side, you can see two histograms. They are not really that meaningful. All I want to say here that there is a little bit of appearance of Julia. So if you look at the plots at the very beginning, okay, GitHub started somewhere here, 2010 or so. So this shows the number of repositories which are created by people who has forked the CMS SV SW package. So those are people who are very likely HEP users. And you can see that on the lower plot, I excluded Python because it has a really big bars. You can see that Julia is slowly arising. So there are some packages which appear in 2014, 16, 18, etc., etc. So there is some appearance of Julia. And if you look on the right side, these are people who are probably data scientists or more related to data scientists. So I scraped the users who are forking NumPy. And it's also interesting because there is even more Julia present. And what's even more interesting, that Rust is really taking off. So this really surprised me. Apparently, it's going to overtake C++ very soon. So there's some shift there. Maybe not too much Julia, but at least a lot of Rust. And I think we should change this for Julia at least. Okay, so the question is now, which language would you have picked in 2013 if you had to choose from today's programming languages? And we think, with we, I am referring to the authors of the paper I will show you later, that Julia is a very suitable candidate. So it's a high-level language, which we have already seen. It's easy and interactive without much penalty or any penalty on the performance. On the right side, you can see this very simple graph where I distributed these languages like Julia, Python, Fortran, C++, and also the Python language combined with like C++ bindings, etc. And I think that if you pick Python, of course, you would put Python somewhere here. So Python alone is slow, but very easy. And Fortran is, of course, on the top right side. It's hard and fast, together with C++. And also also Python combined with some C++ code, etc., is probably hard, but it's fast. It's probably not as fast as C++, but somewhere here. So maybe I should put it a bit higher. But yeah, it should sit somewhere there. And Julia is in the top left corner. I think it's fairly easy to get started. And this I have some evidence because I supervised a few students who started using Julia during my supervision and ended up producing really nice packages which are still in use and which could be taken over by other people easily. In contrast to Python, where people write code which is, even if we supervise them, it gets really hard to read after a couple of iterations if you want to make it fast, and it's also not so easy to extend because you need to mix it with other stuff. Of course, in high-energy physics, you cannot waste computing power. and we need to often process terabytes of data. So doing this with Python only is of course not possible. So you need to do some things there, and we all know this problems when someone starts to utilize pandas to open big files and then do some random copies and unnecessary temporary copies, etc. Okay, so we have this interface with legacy code written in different languages. This is also one of the requirements, which is very present in the high energy physics world. We have a lot of ancient code, which we still need and which is good. And why should we throw it away? We can easily use it with Julia. And of course, parallel and distributed computing, which are kind of core features of Julia, together with the ability to write even GPU kernels in native Julia, which is not fully possible, but it's so it's a bit limited, but it's possible. I will not cover this in this talk, but if you are curious, you can come to me afterwards. Okay. By the way, the most loved languages here, I'm not sure if you can read it, but Rust is with 86% on the first place, and Julia is at the fourth place with 72%, followed by Python with 67%. So I think this is also a nice language, let's call it feature. Okay, Julia's native speed compared to C and Python. Of course, native speed is always interesting, but these micro benchmarks are not really that good. But I still show them. So I think to compare language speed, there is much more things. There are much more things needed, like full analysis stuff, which we also did in our paper. But this plot clearly shows that Julia is fairly constant with the speed and very comparable with C. So there's this micro benchmark site which you can watch at the Julia lang site. What you can see here more or less is that code naively written in Julia is often close to peak performance, and this is also what I observe when I do code reviews on people who start working with Julia. It's usually really a big difference when people come to me and say, oh, can you look at my Julia code? I'm beginner and maybe I can tweak something. Then of course we can often squeeze out like a factor of 2 or maybe even 10 or so. In contrast to when people come to me with their Python code where they use pandas and NumPy and whatever, and they ask me to make it faster, then I say like, okay, how much time do you have? Like 1 hour, 2 hours, or do you have 2 weeks or so? And then if we dive in and utilize NumPy and whatever, then we can really make it fast, like orders of magnitude faster. If not, then yeah, it's mostly very far away from the native speed, from the speed limit actually. Yeah, and yeah, one of the bigger problems, of course, is that I mentioned before that physics students do not have computer science education, so they often approach problems very naively. So when they see a tutorial where someone writes a for loop to solve a problem like sorting or so, the first thing the student does is implement their own sorting and then sort the events with the sorting function or whatever. So they don't realize that this is really extremely slow in compared to when you go to a fast type static language. And of course, memory issues, which is a very big deal. So if we work on cluster systems, many times the memory is quite limited, or at least big memories are or a bigger memory access is only allowed on a smaller set of the computers. So you often have to deal with something like 8 or 16 gigabyte limits. And if you do these whole meal operations in the Python world with pandas or NumPy or things like this, you can quickly hit these memory limits because you need to think vectorize. So this is this bad scaling, which I was mentioning here. And this whole meal programming, like trying to load the whole file and trying to load the whole data frame in once and not doing these iterations, etc. Okay, and by the way, I like this quote, Julia, a language that walks like Python, runs like C, from K.S. Kupusami. I think that covers it very nicely. Okay, one thing which is of course always important, and this is the entry point to the experiment usually, is accessing the data formats. So we have a lot of different data formats in HEP, but one of the most prominent ones is of course root. So even if KM3net, for example, of course, is a neutrino detector, so it does something with high energy physics, but it's not this typical high energy physics collider experiment, or how you want to call it. We still use root. Why? Because people from CERN started Antares, which was the predecessor of KM3net, and then they started to work on KM3net, and they already knew root. So they brought new root to Antares and then to KM3net. So now we have to live with it, even if our data is not that complex compared to like CERN experiments, which have like multiple layers, multiple detectors around the vertices. We only have PMTs, which are sitting in a 3D grid and measuring a signal, which is represented by a single byte at a given time, and that's it. Still, we use root. And then, of course, all the Monte Carlo simulations, which are then nested, also use root because people are used to root and brought it to our experiment. And there, of course, root is also really nice because nested data is one of the main aspects of the root file format. So most of the popular data formats used in HEP are supported with native Julia packages, with a little bit of caveat, like we cannot write root files, only through the Python package uproot, for example. But we have this entry point, so we can open files, we can do something with them. And Julia can also be used to introduce other formats to HEP, which are maybe not so popular. Like we like to use in KM3net HDF5 also. So yeah, we can write them, of course. Okay, high-level interactive coding, so without penalty in performance. This is the subtitle. This has a long history in HEP. So it was introduced in the 80s by Paul at CERN, and then later in root, of course, we all know this stuff. And this is something which makes it a little bit easier to work with root because you can just open it and then play around. Of course, it's a bit hard to get used to the errors and how to learn how the framework works. But there is interactivity, and yeah, as I said, it has a long history, and we also need it in science. It's really nice to have something iterative when you work on your analysis. And Python also popularized the REPL, the read, evaluate, print loop. In other scientific fields, not only in the high energy physics, is it something which is nice, but also other scientists found it nice. And of course, with Julia we have the same interactivity, which we already have seen. And yeah, there's again, I wrote without any penalty. That's not fully true, but with very minimal penalty on performance. So we can do interactive programming in the shell, and we get immediate feedback with that. And then, of course, we can use this type inference feature of Julia to do generic programming, which we have seen a lot of time today. And of course, the Jupyter Notebook support. So all this is also given by Julia, by this language. One thing which I think is extremely helpful, which also Stefan has mentioned, is the code reusability and extensibility. And also this expression problem, which Stefan mentioned. I don't want to do like too much detail on it because we are running out of time. But you should really, I even quoted his talk, which he mentioned before, the unreasonable effectiveness of multiple dispatch. You should really watch it. It's like 30 minutes or so, but it's nice. And one of these slides is this one. It shows how two packages like differential equations and measurements play together without knowing each other. So measurements is a package where you can define your values with errors, and differential equations is Chris. He's our man, one of the brains behind differential equations. So obviously it can deal with differential equations, and if you combine these two packages, they really don't know each other. But if you put these values into this software package, it knows how to deal with it because the basic operations were defined. So it's just doing some error propagations and all the stuff. And even if you can combine it with plots, you can see the error bars in the figures. So this is, I think, very nice that people can simply work on something and extend something without the need to download this package and then modify code in this package. So that's what Stefan meant with I can add functionality without touching existing code, or I can add new types without touching existing code. Exactly. So interfacing legacy code, I have already said that we have some old code in HEP, which is extremely useful, and we don't want to throw it away. Julia has supports native call into C and Fortran. You can use the C call method, which is very nice. And there is also the possibility to wrap C++ code. This will be heavily used in Giant 4, which Felipe will show us on Thursday at 11:20. And we even have zero overhead Python wrapping if you use PyCall, or there are a couple of other alternatives. So in the right side, I screenshotted in a session where I'm using PyCall to import NumPy as NP. And from here on, I can simply call it just like Python. So if you happen to have some Python package which you don't want to rewrite completely in Julia, but you want to work with it in your Julia session, you can just import it and work with it and write your test and whatever, and then simply replace all the Python stuff in Julia. Okay. So yes, one more thing, but I can almost skip this because Stefan, I also wanted to show a live demo, but Stefan already covered this. Julia's packaging and distribution system. Just let me tell that this is really awesome. So you have these reproducible environments with exact versions of all dependencies in Julia. So this is really a built-in feature. This is nothing like in Python, where this has been predefined. Like every year there is another way to package your stuff, or define dependencies, or install packages, etc. So this is really cool in Julia, and you can also have your own private package registries if you want, which you can also have with Python actually, but it's much more sophisticated. And the distribution of pre-built binaries of external dependencies. So this is something which the Conda system does. So if you want to install something which depends on some C library like the HD5lib on Python, for example, PyTables or H5Py, they need to have some access to this library on your system. So either you install it beforehand and then you set some environmental variables, or discovered by accident, or you have to use something like Conda. And in Julia, you have the distribution of these so-called artifacts, which are pre-compiled binaries. So you get this stuff automatically downloaded when you install the package. So no need to use Conda, or no need to compile this stuff by yourself. You can, of course, but you don't need to. And of course, we have this large combinatorics of OS architectures and compiler features, which is very, very easy to use them. So here's, again, these reproducible environments, which is in science extremely important. There are these two configuration files related to the dependency management. What Stefan already showed us is you have this project toml, which defines only some loose constraints, some of the top level dependencies. No versions, just the names of the packages and their unique identifiers. And this is sufficient if you have some software package or library which is meant to be combined with other software. And then the package manager will use this information in this file to determine the most suitable versions of all the required dependencies. And then you have this manifest toml, which contains all the dependencies and all the sub-dependencies, etc. So all the trees, including all the compiled, even non-Julian binaries, with exact versions to be able to fully reproduce the environment. And this is mandatory for scientific analysis to be able to reproduce their results. We will have a talk from George later at 4 p.m. who will show why this is important. And the private registries, this is just a very tiny example. We have a small public KM3 Julia registry. It only has like 10 packages or so. But it's really cool because you can simply add this registry to your own registries, Julia registries. And from then on, you can install KM3net related packages just via add and the package name. And the dependencies can spread over multiple registries, just like Stefan mentioned. And yeah, they also work seamlessly. So the private registry can work with the SSH key authentication in the background. So it's Git based, not like the PIPS simplified web server approach. So you may know that you can also have your own package repository in Python. But it holds the source code of the packages. And in the case of Julia, it's really a Git repository with all the metadata. So there is no software stored here. It's just the metadata with pointers to the Git repositories and the hashes. Okay, so last but not least, parallel and distributed and GPU computing. So built in or built for, you can choose whatever you want. Loops can really easily be parallelized by adding a keyword. Stefan also showed this. So if you do something like for event in my tree and then process the event, which is very common in the high energy physics world, you can put threads in front of it, and then it becomes parallelized easily. But there are more sophisticated tools also, which I will not cover in this talk, but just to mention that if you are really curious about low-level parallelism or SIMD optimizations, those can be used in Julia quite easily. That was a nice chat talk from Grim at Julia. So if you want to go there, you can have a look at the slides. And yeah, an impressive example from kernel abstractions, which allows Julia code to be passed as a kernel function to GPU. So this is also really cool, what I mentioned earlier. Okay, so I think that's it. Last slide, I just want to make a little bit of advertisement to for our paper, which we published a few weeks ago. You can find it in the Computing and Software for Big Science journal of Springer. And yeah, here's the DOI link also. So there we discuss a bit more details about the Julia language. So yeah, we think HEP is ready for Julia. The question is, how do we propagate this idea? How do we propagate it to students and also to the older generations? Okay, thanks.